problem 3, which says there is an atom of atomic number z equals 25. What is the radius of an electron in the n equals 3 orbit? What is the total energy of this electron? So what we want to do here is, first quickly, I want to develop the equation of an orbiting electron around the proton. I want to use the Bohr model of the atom. This is a simplistic view, so we're not going to take into account all the quantum effects. So that would take more quantum physics and a more advanced physics. So let's develop the equation of the radius of an electron and the energy of the electron. So after that, from then on, you could actually use those equations every time you see this kind of problem, right? The nucleus has a bunch of protons. Proton, 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 proton. And the number of protons is the atomic number Z, right? So that's Z. And then you have an electron at the farthest orbit. There are also Z number of electrons. The electrons interact with each other. But I'm going to ignore the effect of the electrons on each other, okay? Focus on the effect of the protons on the electron, causing the electron to go around, right? So what would the force on the electron be? So the electron is going around. So the force would be K is from Coulomb's law, and then you have here Z number of protons. So you have ZQ. That would be the total charge of the protons, and then the charge of the electron is also Q. We could write E for the symbol E. So ZE is the total charge of the nucleus, and then the charge of the electron is E, right? So all of those protons are causing the electron to orbit around the nucleus, divided by R squared. So that's the total force, and we know from physics 1 that the force is equal to the centripetal acceleration, right? mv squared over r. mv squared over r. So from this, what do we get? Z, K, E squared. And then one of the r's cancels over r is equal to mv squared. Okay? So this gives us a relationship between the radius and the velocity. Now, what else do we know? From a Bohr's model of the atom, right? We know that the angular momentum of the electrons has to be quantized. So it's equal to mvr, which equals to nh over 2 pi. Right? Discussed about that when I went through the questions of the addendum. So if you watch those videos, you can see my explanations of these. So then this also gives us a relationship between velocity and the radius. So what I want to do here is substitute for one, say for r, okay? So from here I can say r is equal to nh over 2 pi, and then mv goes down there, right? Then I take that and I put it into this r, right? So you have k z e squared over, and then you put this whole thing, nh over 2 pi mv, and then that's equal to mv squared, okay? So what is this going to help me to do? Well, if I multiply this over there, k z e squared mv squared, and take this whole thing over there, nh over 2 pi mv. Okay, well, m cancels, one of the v's cancels, and what do you have? Well, you actually get an expression for, let's write this here. And the n also cancels, right? So the n cancels with the m. One of the v's cancels with the v squared. And then what ends up happening? Well, let's write down what we have here. K z e squared is equal to, we have a v, then we have nh, then we have 2 pi. the m's canceled, one of the v's canceled, right? So therefore, the velocity here is going to equal what? Velocity equals, the 2 pi goes over there, 2 pi k z e squared over nh. So now, from that equation, we could also come up with the equation for the allowed radius of the orbit and the allowed kinetic energy, potential energy, total energy, right? Usually the most important thing that we are interested in is the allowed radius of the orbits and the allowed total energies. The radius of the orbit and the total energy. Because those are the ones that we use most often, not the velocity, right? So remember the radius was nh over 2 pi mv, so that means radius will be nh over 2 pi m, and then this v that we have, so that's going to give us 2 pi kz e squared over nh. Wow, that's a full load, right? So what is that equal to? Well, nh goes to the top, and you end up having r is equal to n squared h squared over 4 pi squared m k z e squared. Okay? All of these things are constants. So we can actually substitute these in and come up for what the equation is, except for n. N is the allowed orbits. N equals 1, n equals 2, n equals 3, n equals 4, right? So then we have r sub n, Planck's constant, 6.626 times 10 to the minus 34. We got to square that. 4 pi squared, this is the mass of the electron. 9.11 times 10 to the minus 31. This is K from Coulomb's law, which is 9 times 10 to the 9th. And then Z, well, Z is just Z. It's the number of protons. And then this is the charge of the electron. 1.6 times 10 to the minus 19 squared. Okay? So what is that going to equal? The radius is equal to, well, you get a bunch of zeros, right? But if I change that to scientific notation, you're going to see what this is. What you get in scientific notation? 5.3 times 10 to the minus 11 meters. And then, of course, there is this term, n squared over z. N squared over z. Okay? Usually the way that this is written is this way. R sub n 0.053. You go 2 decimal places over. 0.053. N squared over z. Nanometer. Why? Because nanometer is 10 to the minus 9. So you go 2 places over, subtract 2 from this. So this is the radius of the allowed orbits of the atom, okay? Of the electron in the nth orbit. So notice that as you go from n equals 1 to n equals 2, you go from n equals 2 to 3, the allowed radius is a proportion of the square. So they get, like if you go from n equals 1 to 2, the distance goes by a factor of 4. When you go from 1 to 3, you square the 3, you get 9. So the third orbit is 9 times farther away. You go to the fourth orbit is 16 times farther away, right? And then, of course, the more protons you have, Z, that tends to decrease the size of the atom. So, because it attracts the electrons more, so if you have more protons, the radius is less. So let's calculate that part of the question. In our case, Z is 25, N is 3, so what is this going to be? R of 3.053. We're going to put N is 3 here, square it, and then we're going to put 25 for Z. 25, and then this is going to be nanometers. So, just remember this final equation then. So 0.053 times 9 divided by 25. So then it's going to be, radius is going to be 0.01908 nanometers. So now let's develop equations for the energy. Okay, remember what the velocity equation was? It was 2 pi kz e squared over nh. Okay, so what's going to be the equations for the kinetic energy? The kinetic energy is equal to one half mv squared. So the velocity, if you square that, you have 4 pi squared k squared z squared k squared z squared e to the fourth, e to the power fourth, divided by n squared h squared. Okay, so we can put all of that in. Now what's going to be the equation for the potential energy? The potential energy is going to be the interaction of the electron with the proton, right? That's equal to negative kze times e over r. Okay, and then we could use the equation for the r to n squared h squared over 4 pi squared mkz e squared, and then you put that r over here, you're going to have n squared h squared over 4 pi squared mkz e squared. Okay, now what's going to end up happening? The potential energy is going to be negative and then kz e squared. All of these things go to the numerator. So you have 4 pi squared mkz e squared divided by n squared h squared. So the potential energy is going to be negative 4 pi squared m. K, you have 2 of the k squared. You have 2 of the z's, z squared. And then you have e to the fourth over n squared h squared. Okay? Now notice that the potential energy has the same looking form as the kinetic energy. The kinetic energy also has an n, 4 pi squared, k squared, z squared, e to the fourth, e to the fourth. It also has n squared, h squared. The only thing, it has an extra half here, and then this one has minus. So what's the total energy? So what ends up happening is that the total energy is basically this part of it is the same as this part of it. Okay? So basically you end up having, it's like saying half of something minus something. Like half of this thing, let's call this something x, right? Minus this thing, which is x. So what is it going to be? It's going to be negative half x. So your final answer is going to be negative half of that thing. E total is going to be negative, this whole thing divided by 2. 4 pi squared m k squared z squared e to the fourth over 2n squared h squared. Well, this 2 will cancel this, and then you end up having 2. Now let's put all of the constants. Negative 2 pi squared, 9.11 times 10 to the minus 31. Put 9 times 10 to the 9th. Square it. Okay? Which we can't do anything with. We have the charge of the electron, 1.6 times 10 to the minus 9, 19 to the fourth power, divided by n squared, and then Planck's constant, 6.626 times 10 to the minus 34 squared. So let's go through it again. So you end up getting what? E total is negative. This negative comes from here. So the total energy of the electron in the nth orbit is negative. Well, what does negative mean? Negative means it is bound to the nucleus. It's not going to be thrust, right? So you want it to have a negative energy. So negative, and then the final answer, 2.1743 times 10 to the negative 18. Then you have z squared divided by n squared. Okay? Now, usually the way that this is written is it's converted into electron volts, because this unit is in joules. So how do we convert to electron volts? Okay? What's the conversion? We say 1 electron volt is 1.6 times 10 to the minus 19 joules. So our answer was negative 2.1743 times 10 to the minus 18 over z squared over n squared. This was in units of joules. And then we say 1.6 times 10 to the minus 19 joule is 1 electron volt. So divide the number that I got by 1.6, divided by 10 to the power negative 19, I get I get negative 13.59 z squared over n squared electron volts. Now, the good thing is, once we derive this, and then once you go through the derivation, understand the process that we took, you don't have to keep rederiving it every time you see a problem like this. You can then again use the energy equation like this. This is the total energy of the electron in the nth orbit. Okay? For the hydrogen atom, what would we do? We would use Z equals 1. And this gives us pretty good approximation, particularly for the hydrogen atom. Okay? And then we would just put Z is 1. For the other atoms, we put whatever their Z is. So in this case here, there's an atom, atomic number Z is 25, n equals 3. What is the energy in the third orbit? So now we could put it all in. E total, nth, negative 13.59. So we take the 25, square it. So what this is saying is, when you have more protons, the energy goes as the square of that proton interaction with the electron. And then the energy also decreases as a function of 1 over n squared. But actually it increases. Why? Well, because as the n gets bigger and bigger and bigger, the number becomes less negative and less negative, right? Because it starts out really, really negative, then it becomes less and less negative. As the n goes to infinity, the energy goes to 0. That means it's no longer bound to the proton, right? So now we divide that by 3 squared, okay? So negative 13, so E total in the nth, negative 943.75 electron volts. Okay, so the electron in the nth orbit, in this case it's the third orbit, has a total of energy of negative 943.75 electron volts. Okay, from there, the next problem I will show you what will happen if this electron makes a transition from one orbit to the other orbit, and it's going to emit a photon of a certain wavelength. Okay, thank you.